Okay. So one answer for 23, 1 and 2 quiz is that current flows. 2 is parallel, which we've had that word before. 3 is series, we've had that word before. 4 is the same or constant or some sort of thing like that. 5 is sum, so is 6. Sum. Question about scoring things. Number 1 again is that current flows. Yeah.
I actually want to say I completely guessed on number 1 and I got it right.
There you go. You're a good guesser. It's a good life skill.
Number 6, that's true. No, it's right.
Score stuff.
That's what I said.
Well, let's do a combination of explain, prep you for the math, and just set up for our chapter and preview what's next. So the next read is 23, 3 and 4. There's going to be 10 points off of that. Question 1 stays the same. Question 1, for a circuit to be complete just basically means the wires are all connected and everything's turned on. So if you get your wires all connected and things are turned on and nothing is broken in any way, current is going to flow. So right now we have a circuit that's complete to turn on this light and that light and this light and that light and this light and this light and this light and this light and that light. Lots of lights. Parallel versus series is going to be a discussion throughout the chapter. This reading had more to do with series. The reading you'll do tomorrow has more to do with parallel. Parallel is if you have a break, it's only going to stop the current in a piece of it. If you have series, if you have a break, it's going to shut down the whole thing. So let's think about my lights in this room right now. So let's say one of these light bulbs burns out. Is that going to shut down all the lights? No. So what sort of connection do we have going on in this room with the lights? Is that parallel or series? That is parallel. Can anybody think of an example from your life that you've encountered a series type of electrical circuit where if something goes out, it shuts the whole thing down? Some Christmas lights, like stupid Christmas lights. Sometimes you buy those stupid Christmas lights, and if one of the lights burns out, the whole thing stops working. That would be an example of series type wiring. Last chapter, when we took the test, we had 2 pieces of equipment that I can't talk about because right now somebody's making up a test, but we had 2 pieces of equipment, one that was connected in parallel and one that was connected in series. But I think you're going to need those examples and the definitions next time. So, yeah, it'll say name 2 kinds of circuits, so parallel versus series. Define them. So parallel, you'd say that a break is going to stop the current only in part of it. Series will say a break stops the current in the whole circuit. And then it'll ask for 3 follow-up facts that we're going to grab from 4, 5, and 6. You don't need the example this time, but I bet someday you'll need the example. Parallel wiring is pretty much anything in your house. If your house was connected with series wiring, if you wanted, let's say, to go in the kitchen and turn on the blender, what would you have to do to run the blender? Yeah, and literally everything. You'd have to go in, and if you wanted to like do some toast, you'd have to like not just do your toaster, you'd have to turn on every appliance in your kitchen if your kitchen was wired in series. If your whole house was wired in series together, to run the toaster, you'd have to run literally every appliance in the whole house. Everything that was plugged in would have to be turned on somehow. So you'd have to turn on your hair dryer so that you could run your toaster. I mean, it would be bonkers. But house wiring is parallel wiring. Series would be stupid Christmas lights for one. But the question will be name 2 kinds of circuits, which we did, define them, and then for the old circuit, tell 3 other facts. So the 3 facts are coming out of 4, 5, and 6. 4 will just say current is the same everywhere. we'd say, you could either say the sentence for resistance, that the total resistance is the sum of the individual resistances, or if you'd rather write this, total resistance equals resistance 1 plus resistance 2 plus as many as we have till I get bored. And then you could either say the sentence for number 6, or you could do an equation with the same thing. The voltages are, total voltage is voltage 1 plus voltage 2, add them up as many as there are until you run out or get bored. But 4, 5, 6 you can either do in sentence form or equation form. I'm probably going to prefer equation form. Question about the quiz? Let's check pictures. One of these two pictures is a picture of a series setup. One of them is a parallel setup. What were these called from our diagram last time? Each one of those is a resistance or a resistor. Basically imagine each one of these to be like an appliance. So here we've got electricity going through appliance 1 to get to appliance 2 to get to appliance 3, right on down. It's sort of like a straight line system. This, we've got these like branches kind of branching around. Anybody have a thought on which is a series versus which one's a parallel? Top is series. This is parallel because on this, if I am trying to flow my electricity through here and I break that, are these going to get any electricity? No. We like shut the whole thing down. Envision maybe a comparable situation. You're trying to drive home and there's 3 red lights. And this red light turns red and never changes again. Is anybody going anywhere? No, it's all just going to pile up forever. Okay. This is parallel. Parallel, a brake is only going to stop part of it. Let's say this gets shut down or this red light turns red and we're trying to travel home and this is like our map. We shut this down, can we still flow? Yeah, you're going to see this is all backed up in red, you're just going to go another way. You have multiple options for these branches to flow from. If you remember your diagram we did last time that I can't really say right now, one of the items we put it like right in line. The other item we kind of like created a loop around situation. That's parallel versus series. Tonight's homework is all series stuff. So let me do some numbers to just illustrate like what's going on with this. So let's say I have a 30 ohm resistor, I have a 10 ohm resistor, I have a 20 ohm resistor, and I want to know what is the total resistance. Theory? 60 ohms is correct. Because we learned that the total resistance is the sum of all the individual resistances. Each one of those is just going to get added up. If I tell you we have a 120 volt battery connected up here or a 120 volt electrical line hooked up to make some electricity flow and run this stuff, I could ask you then what the current is. What's our old equation? What did I equal? V over R. That is still here. So in this circumstance, the I is going to equal the 120V divided by the grand total R of 60. So what is the current? 2 amps. This is going to get 2 amps. This is going to get 2 amps. This is going to get 2 amps. That's just going to be the way that goes. I'm not going to get too far involved into the parallel because it's more what you're reading about tomorrow. But if we give this circumstance 30 ohms, 10 ohms, and 20 ohms. Anybody care to speculate where more of the electricity is going to run? No. Right idea, but wrong direction. It would want to run through the one with least amount of ohms. Picture resistance in the electrical world almost like friction in the real world. Like friction slows things down, makes it harder. If you have 10 ohms of resistance, you have not that much resistance. 30 ohms of resistance has way more resistance. So if you have electricity flowing and it's presented with 3 paths, I don't know if you've ever heard the phrase, take the path of least resistance. Like that applies to life as well as electricity. If electricity is rolling and it's presented to paths of 30 ohms, 10 ohms, and 20 ohms, some will take each path, but more electricity is going to take the path of which one will handle the most electricity? The middle one. The 10 would take the most. It'd be like if you go get in line at the store. There's 30 people in this line, 10 people in this line, and 20 people in that line. Which line are you going to pick? You're probably going to get in the 10 line. There's less resistance to you there. But parallel, it's going to be a different scheme. 30, 10, and 20 tomorrow will not make 60. Every time you create a new path to flow, it gets easier or harder for the electricity to flow. Easier, because there's more paths. You know, you're at Walmart and they open you up another lane. Is it easier or harder for you to get through line? It's easier. There's another line. Here, every time today, in today's homework, every time you add a resistor, the resistance goes up. But for the parallel tomorrow, every time you add a resistor, the resistance will go down. But I'm not going to go too far into that because that's, again, you can read about that for yourself. In terms of voltages, let's rework this equation. You're going to be, in this chapter, better to not like do algebra every time, but just write down a new version of this equation. What does V equal? If I equals V on top of R, what does V equal? I times R. So in this little piece of the world, V equals I times R. What's the I in this part of the world? Two. The resistance just in this part of the world? 30. So how many volts are in this little part of the world? Take 60 volts to run that thing. Over here, V equals, what's the I? 2. What's the R? 10. So how many volts are in this part of the world? 1. If we go over here, what's the I? 2. What's the R? 20. So volts in this part of the world? 40. What can we do to check our 40, 20, 60 thing to be pretty sure that that's like what we wanted to have? Add it up to 120. We had a 120 volts worth of electricity. 60 volts is going to do this, plus 20 for the littler thing, plus 40 for the medium-sized thing. Altogether, those should add up. So again, the 3 facts you're talking about tomorrow is that current is the same everywhere. We're talking about the total resistance is the sum of the little pieces. 30 plus 10 plus 20 makes 60. And we're talking about the voltage is the sum of the little voltages. This plus makes the 120. This equation still largely runs your life. But homework tonight, your first objective will be find the total resistance. Second objective will be find the current, which is the same everywhere. And then maybe if you have a third objective, it's going to be to figure out the little mini voltages. There's a homework 1 to 12 that has you doing that. That's pretty much it for series. Again, one more time for series, what was the same everywhere? Current. Tomorrow, current will not be the same everywhere for the other circuit. Something else will be the same. Other things will be different. But today, current's the same everywhere. Voltage, resistance, they're different here, there, and everywhere. You have some adding maybe to check your life out. Anybody, something that I can clarify about the series circuits?
So, this is just for the quiz. So, like, there's no one that stay the same?
So 1 stays the same. Yeah, there's 10 new ones. 1 stays the same. And then 2 through 6 become 7 points. Name 2 of them, define 2 of them, and then 4, 5, and 6 describing either with a sentence or more likely with an equation. Anybody else, anything about what's going on as we step from 23.12 up to 3.4? Okay, we'll shut that down.